Okay, so we are still looking at pH of mixtures. We're going to look at a different example though, strong acid and strong base. It's a little different. We're not going to add the moles of hydrogen concentration together. So this should be a neutralization reaction. We're going to have to balance our chemical equation to solve because it does matter if we have a 1-to-1 ratio, 2-to-1 ratio, 1-to-2 ratio, whatever it may be. The steps to solve are kind of similar but a little bit different. We're going to write and balance our chemical equation. Obviously, we have to start there. We're going to find moles of the acid and the base. We're going to figure out which one is limiting based on the mole ratio. We're going to find the excess, so whatever is left over is going to tell us what the concentration will be, if it's going to be a base or if it's going to be an acid, and what that pH or pOH will be. And we're going to be using our log function to be able to calculate using that. So we are going to do a couple of examples. First one is going to say, what is the resulting pH of a mixture prepared by combining 20 milliliters of 0.07 molar NaOH and 13 milliliters of 0.09 molar HCl. So we have to start with a chemical equation. We're going to write that out. We have our sodium hydroxide, NaOH, plus our HCl, hydrochloric acid, yielding, it's always going to yield a water, we should know that, and an ionic salt. It's a neutralization reaction. Since sodium and chlorine have a 1 and a 1 charge, we're just going to have subscripts of 1s, which we're not showing anything. And if you notice, we have a balanced chemical equation already. So each of these are going to have a coefficient of 1, which makes our math easy in the long run. We do have to figure out the moles of both our acid and our base first. So we're going to use our volume and our molarity. We have 20 milliliters and 0.07 molar that are going together for NaOH. So we're going to change that milliliter into liters. We have 0.020 liters and 0.07 moles of NaOH for every 1 liter. Okay, so if we are going to multiply those two together, we are going to end up getting 1.4 times 10, 1.4 times 10 to the negative 3. Let's fix that for a second. There we go. And that'll be moles of NaOH. And then we're going to do the same for our acid. We have 13 mils of 0.09 molar of HCl. So we have 0.013 liters and 0.09 moles of HCl for every 1 liter. Okay, so we're going to multiply those two together. We get 1.17 times 10 to the negative 3 moles of HCl. Now, we have a 1-to-1 ratio in our equation, which means these are the exact amounts that have to be used. And so we can compare them and see which of the two are smaller. 1.17 compared to 1.4 is a smaller number, so our HCl is going to be our limiting factor. And there will be some NaOH that is going to be left over. So since we're going to have some NaOH left over, we're going to subtract the number of moles of HCl from the moles of NaOH to see how many moles of NaOH are going to be remaining. Because for every 1 mole of NaOH, I have to have 1 mole of HCl. So that really means that 1.17 times 10 to the negative 3 moles of NaOH are actually being used up in this process. So we have 1.4 times 10 to the negative 3 minus 1.17 times 10 to the negative 3. We subtract those two from each other, we get 2.3 times 10 to the negative 4 moles of NaOH left over. Now, since we have a 1-to-1 ratio, since there is 1 hydroxide in NaOH, we are going to go ahead and say that there are really 2.3 times 10 to the negative 4 moles of our hydroxide ion. Because there's only 1 hydroxide in NaOH. So if we set up a conversion table, we would find that there are 2.3 times 10 to the negative 4 moles in there of the hydroxide concentration. So we would put and find the concentration of hydroxide by putting it into our molarity equation. So let me change colors. We've got 2.3 times 10 to the negative 4 moles over our total volume. So our total volume is going to be 20 milliliters plus 13 milliliters. So that's going to be 33. So we have 0.033 liters going into our molarity calculation. So that comes out to 6.97 times 10 to the negative 3 molar. We can only keep 2 sig figs. Technically, the 20 is going to hold us back. There should be a decimal there. We're going to keep 2 sig figs, and the third one is going to determine if we're going to round, which we will. So we have 7.0 times 10 to the negative 3 molar for our hydroxide concentration. So we are going to use that to find the pOH. We can't find the pH from a hydroxide concentration. We can only find the pOH from a hydroxide concentration. So pOH is going to be equal to negative log of our hydroxide concentration, 7.0 times 10 to the negative 3. So we're going to calculate that, and it's going to give us 2.1549. If we have 2 sig figs in our log number, we are going to use 2 decimals in our pH. So it's really going to be 2.15 for our pOH. And remember that 14 minus our pOH will give us our pH. So we are going to do 14 minus 2.15 to get 11.85 as our pH. Now, we could have done the constant for water, the ion product constant, and divided by the hydroxide concentration. So we could have done 1.0 times 10 to the negative 14 divided by 7.0 times 10 to the negative 3 to get the hydrogen concentration, and then done the pH of that. It should give us the same answer as what we got for the pH though. So either way that you do it, it should give you the same answer or one that's within a decimal, so it shouldn't be anything completely different. And this solution, because it has a pH of 11.85, is going to be considered basic. So let's go to our next example. It says, what is the resulting pH of a mixture prepared by combining 24 milliliters of 1 molar H2SO4 and 36 milliliters of 1.5 KOH? So we're going to find our moles. Go back to blue. We're going to find our moles for both of our acid and base. Using our information from our question, we have 0.024 liters of H2SO4 with a 1 mole per 1 liter situation. So we have 0.024 moles of H2SO4. Okay, then we have 0.036 liters or 1.5 moles per 1 liter. So we multiply those together, we get 0.054 moles of KOH. Now looking at it, you would want to say that H2SO4 is the limiting reactant because that number is smaller, but you have to remember that H2SO4 is diprotic. So whatever we have in KOH, we have to have twice as many H2SO4 concentrations, or moles really, to be able to see which one is limiting. So if we were to multiply 0.024 times 2, that would give us 0.048 moles, which is still less than 0.054 moles of KOH. So H2SO4 is going to be our limiting in this situation. So we're going to have some leftover KOH. So for every 1 mole of H2SO4, I have 2 moles of KOH. I did not want to put that 2 on there. Let me get rid of it real quick. All right. For every 1, I have 2. So that means for every 1.024, I need to be using, in this situation, the 2 to be able to neutralize our KOH. I'm going to be using 0.048 moles of H2SO4 really in this situation, which means that 0.048 moles of KOH is going to be used up. And so we're going to use our number 0.048 and 0.054 to figure out how many moles of KOH is going to be left over. So since it takes 0.48 moles of KOH to neutralize this situation, we're going to subtract that amount of moles from the total amount of moles that we had of potassium hydroxide. And we're going to get 0.006 moles of KOH left over. Okay, so if we have 0.006 moles of KOH left over, or 6 times 10 to the negative 3, we're going to use that to find the molarity of OH, because for every 1 mole of KOH, I have 1 mole of OH. So really this is 0.06. Those decimals are important. Moles of OH, or hydroxide ions. So we're going to find the molarity of that. So we have 0.06. See, I'm doing it again. Let me change colors actually so we can see this differently. 0.006 moles of hydroxide over our total volume. Total volume is 24 milliliters and 36 milliliters, which gives us 60 milliliters. So we get 0.060 liters, and our answer is going to be I got 0.1 molar of hydroxide. So, let me check that real quick because that seems like it's crazy. 0.006 divided by 0.06, yes, 0.1, okay. So, since we have that concentration, we can figure out the POH again by taking the negative log of our concentration, which is 0.1. And that will give us a 1. Okay, we have 2 sig figs in our log number, so we have to have 2 decimals in our actual pH number or POH number. So it's 1.00. That means that our pH, change to green, 14 minus our POH gives us our pH. So 14 minus 1.00 gives us 13.00. as our pH. So it's going to be an extremely basic solution. So we are going to use that function and that way of calculating to be able to determine the pH of a mixture of an acid and base. So you do have to make sure that you're paying attention to the diprotic or triprotic acids and taking that into consideration with that mole ratio. So whatever your limiting was in the bottom left corner, we said for every 1 H2SO4, I have 2 KOHs. H2SO4 was our limiting here, so we ended up figuring out that if I'm using 0.024 of H2SO4, that limits me. I'm going to have to use 0.048 of KOH to be able to neutralize the entire situation. So please make sure you're doing that mole ratio appropriately, and you are taking into consideration the subscript on either your H or your OH concentrations. So that kind of wraps up our pH of mixtures. Make sure that you guys are doing some practice problems on your extra practice, and I will see you guys tomorrow.